All right, here we are yet again for a follow-up session. This is going to be part 3 of the lecture. Had a little bit more than I wanted to cover than I had time for, so I'm going a little bit after hours for a part 3 of this lecture. Hopefully nobody comes into this lecture hall while we're working. But it should turn out all right. So I want to continue discussion and finish up discussion on tangential and normal components of motion. So let's pick right up back where we left off. And so let me draw a diagram here. So here, I'm going to define my motion like this. I have my x and my y. And notice, it is important to realize that the x and the y motion are not the same thing as the tangential and the normal components. These are completely independent. So I could have a particle traveling along a certain path with a p and a p prime. And then I could have components ET, ET, and EN, and then ET prime and EN prime, and EN prime. EN prime. And so to do this, to derive the acceleration vector, in tangential and normal components, and normal components, define the motion as in the figure, as shown here, as shown. And so I'm going to define unit vectors, ET. So again, ET and EN are not necessarily the vectors, they're the normal vectors. So ET and EN are normal vectors, and EN are normal vectors. Sorry, are unit vectors, I should say, not normal vectors. Are unit vectors at P and P prime. And then when drawn with respect to same origin, which they usually are, hopefully, with respect to same origin, delta ET is going to be equal to ET prime minus ET. Minus ET, and delta theta is the angle between them. Delta theta and delta theta is angle between them. Is the angle between them. So I could have something like this here. If you look at a path, an arc, let me use purple to be consistent. Let me label these out. Something like this here. If I look at ET and ET prime, and actually, you know what, I'm not going to make that purple, because I don't want you to think that this is describing the path of the object. I'm looking purely at the vectors, the change in the vectors. So if I have two vectors, ET and ET prime, there's going to be a delta theta between them. And here's the origin. And there's going to be a change in theta between them, an angle between them. And this would be like a circle of radius 1, because these are unit vectors. So let me do that in maybe green. I just want to be clear that this is not the path of the object. This is just a circle to illustrate the fact that we're looking at changes in angles. Wow, that's a really bad circle. I cannot draw a circle tonight. Something like this, and this would have an arc length, or sorry, a radius of 1, because these are all unit vectors. And then here, if I run through the trig, delta ET is going to be equal to 2 times the sine of delta theta over 2, and then the limit as delta theta approaches 0. So this is how we can start to define our velocities. We're getting closer. Limit as delta theta approaches 0 of delta ET, delta ET over delta theta equals the limit, delta theta, if I can write a theta properly, equals the limit as delta theta approaches 0 of the sine of delta theta over 2 divided by delta theta over 2 times En, and this is equal then to simply En. So, in other words, here, En, vector En, is going to be equal to the change here per theta, det divided by d theta. It is the angular rate in change of the tangential vector. So it is the angular rate of change, at least in terms of the unit vector En. So, okay, so let's look at this a little bit closer here. Same idea, let's draw a different one. Now, if I'm going to draw, let me draw a different diagram. Start on a new page, maybe. X, Y, and this is the path of the object now. So P, P prime, P and P prime, and let's say I have ET and ET prime. Again, these are unit vectors. ET and ET prime. These are not the magnitudes of the actual velocities. They are just these are just the unit vectors in the direction of the tangential direction of velocity, or the tangential, I should say the tangential component. Anyway, then I can define a center of motion for the object, the path of the object here, if it was going in a circle, and the instantaneous curvature is rho. So I know my p's can look like rhos sometimes, but I want this to be a rho, and this to be a rho, and this to be a p, and this to be a p. And then this here is going to be, well, here, delta s, or delta theta. Actually, if this here, the arc length here is going to be delta s, and this is delta theta, and delta theta from our equation of circles is delta s divided by rho. Divided by rho. So then velocity is always tangential, so we can say with the velocity vector expressed as, so I should be more clear with my language. Velocity will not have any normal component, obviously. It will have only a tangential component. So velocity vector expressed as v equals VET, v equals VET, the acceleration vector becomes well, A is equal to dv dt, which is equal to dv dt et here plus v times dE dt, which is equal to dv dt et. So much vector notation, isn't it fun? Plus v times dE dt, dE d theta, times d theta ds times ds dt. Then, but I can also keep in mind the relationship we developed earlier. Det, I think there should be a t here. D theta is equal to En, and rho, then rho, actually that should probably be Vn. Let me double check something here. I think that should be more, yeah, that should be, no, actually I guess I'm okay with that. Just, let me just leave that as E for now. Okay. And rho d theta is equal to ds, and then ds dt is equal to v. Okay, so I know this is not fun, but I guarantee you we won't need to work through much symbolism all the time.
Just go back just 1 second.
Okay. Okay, so substituting then, so we have that, but then after substituting, we get that A is equal to, and this is something actually getting semi-useful, dv dt times et plus v squared over rho, magnitude, times En. And then AT, so both of these then. So AT then is simply dv dt, and AN is going to be v squared over rho. So now we have an expression, and this is not a vector, sorry, these are basically we can say that A is sort of AT times ET plus AN times EN. Acceleration has, this is actually kind of useful. Don't get lost too much in the math. Before, I did want to derive it for the sake of completion, but this is something actually fairly useful. And also knowing that AT is simply the tangential acceleration is simply the rate of change of velocity, and the normal acceleration is the velocity divided by the radius of curvature. And then if you have a, we can also apply this to a space curve, but we'll see that in a bit. So again, the tangential component of velocity, or acceleration, component of acceleration reflects change in speed. So notice we're taking the change of v, which is speed, and the normal component reflects change in direction. So the tangential component of acceleration reflects change in speed, and the normal component change in direction. And the tangential can be positive or negative. Or negative. But the normal always points to the center of curvature. So it can't point outside the center of curvature. It can only be positive if we want to look at it that way. Must point towards center of curvature. So I would also maybe box this one and this one because these are particularly useful. Center of curvature. Next, and this could, so finally let me look at a space plane. That means a three-dimensional plane. This can be three-dimensional. This is the things we described. We're just continuing with this. So our particle is moving along a space curve. So for particles moving along a space curve, just something in 3 dimensions as compared to 2. Well, the a vector, the acceleration, again, is going to be the same thing, except we'll be doing it in 3 dimensions. dv dt, the times et, the tangential normal, is the tangential unit vector. Gotta be careful with my language. Plus v squared over rho, en, and at is going to be equal to dv dt, and an is going to be equal to v squared over rho. So vector, scalar, scalar. And then I can say the plane at any given point the plane containing AV and or AT and AN, AT and AN is called the osculating plane. The osculating plane, and hopefully I'm not mispronouncing that. So I got it spelled right. And the normal to this plane is found by taking the cross product. The normal line to this plane, and this just comes out of Calc 3, is found as, I'm going to let this be vector EB, is simply ET cross EN, and EN here is the principal normal. That means normal relative to the curve, and EB is the binormal. That means on the osculating plane. And by definition, or via the math, because it's two cross products, or because it's a cross product, acceleration has no component along the binormal. Along the binormal. Has no component along the binormal. But we're not going to necessarily deal too much with those, hopefully. Okay, I want to work through one quick example of tangential motion, and then we will call it a night. Okay, So let's see, we have something like this here. Example, consider a car. Let's start with something. So I know this math can be quite scary, but please do not be intimidated if it's been a while since you've seen this kind of math. And I have a car, so given, let's work through the givens. A car travels on a curved section of highway, on a curve, with a radius of 2,500 feet. With a radius of 2,500 feet at a speed of 60 miles per hour. Let's see. At some point they brake. At some point the car brakes. And in 8 seconds, the velocity or the speed has been reduced to 45 miles per hour. And I want to find, so all that was given, find the acceleration of the car immediately after brakes are applied. After brakes are applied. Are applied. All right, so we're going to apply all those fun equations that so terrified us a few minutes ago. And you can see that usually, at least depending on the problem, but when you get down to it, they're actually not that bad. Solution. So the first thing I'm going to do is convert my speed to feet per second. So 60 miles per hour is going to be equal to, so I can multiply by 5,280 feet in a mile times 1 hour over 3,600 seconds. And this will come to about 88 feet per second. And if it was, and then the 45 miles per hour, I can use the same process to go to 66 feet per second. 60 feet per second. Now, remember, we said that the tangential acceleration is going to be basically, or can be thought of as the rate of change in the tangential speed, or the rate of change in the speed. So again, tangential acceleration is rate of change of the speed. So then the AT is going to be simply delta V over T. And notice I'm not using a vector. I'm saying I'm using V I'm using V scalar, not V vector, as my my first speed. So 66 feet per second minus 88 feet per second divided by 8 seconds is equal to negative 2.75 feet per second squared. And then immediately after brakes are applied, so the radius of curvature I can use for the normal component. Again, this was asked immediately after brakes are applied. It would change depending on if it was sometime after. But the normal again, is v squared, the speed over the rho. So that's going to be 88 feet per second squared divided by 2,500 feet, or 3.10 feet per second squared. So I now have the tangential and the normal component of this acceleration. And so I think I'm going to I'm going to plot this out or make a quick sketch in order to illustrate what's going on here. So I'm going to say I have the motion of the object, which is the car in this case. So let's draw it something like this. And right as the brakes are being applied, I have, say, a point A here. And again, motion is along the path here. Now, notice I got a negative value for the acceleration in the tangential direction. That means it's going to be opposite the direction of motion. So this means that AT is equal to 2.75 feet per second squared, foot per second squared. And then AN, of course, is always pointing toward the center, as we discussed, 3.0 feet per second squared. And then the overall V is going to be the combination of these two components. This is the overall A. And did I say overall V? If I did, I meant overall A. Sorry about that. The overall A vector is going to be the combination of both of these components. And this is just simple 2D vectors now. And so I'm going to have a vector, and so again, to describe a vector completely, I need a magnitude and a direction, and I'm going to let that be my theta. Actually, you know what? I have alpha here, so I'll use that. So, fairly straightforward. The magnitude A is just going to be the square root of AN squared plus AT squared, which is going to be equal to the square root of 2.75 squared plus 3.10 squared. Which will then come to A equals 4.14 feet per second squared. And then tan alpha is equal to AN over AT, opposite over adjacent, or here 3.10 over 2.75, which comes to alpha is equal to 48.4 degrees. 48.4 degrees. And so then I can just simply say alpha acceleration is 4.14 feet per second at an angle of 48.4 degrees relative to path. Or behind the car or something like that. Path behind car. So I always like defining, if I define an angle, I always like defining it relative to something, and that could be something as simple as that. Okay, so that will do it for this lecture. Just wanted to go a little bit over time and finish up what I wanted to cover over Chapter 11. Thanks for watching, and as always, thank you.